Hi, everyone. My name is Wayne, and I'm from AMD. And today's session, we'd like to talk about the progress of MST improvement from AMD brought so far nowadays. So today I will quickly go through about the background knowledge of MST and talk about roughly go through the MST flow in Linux nowadays. And then we'll address a bit about the progress of enhancement brought from AMD so far. And then we'll do demo. So why I say MST? MST is the multi-stream transport mechanism that's introduced start from DP 1.2, which leverage the time division multiplexing-like mechanism to have that enable us to enable multiple streams by sharing the same DP link. So these two figures show a common MST topology. One is the DESI chain, and the other one is the traitor-like MST topology constructed by the NST hub. So what makes MST different compared to legacy DP SST transportation mode? That basically that with MST that we need to probe all possible string sinks among the MST topology. And on the second hand, that now we cannot only estimate available bandwidth by local link, DP link training status only, but we also need to understand that the capability of each output port along this end-to-end virtual channel path, especially for the DSC capability. So all the interactions that I just described in previous slide that relies on a lot of different types of cyber messages that introduced in MST, and currently that the DN layer provide helper functions to help different driver vendor to construct all their necessary cyber messages to interact with different MST devices within the MST topology. So let's take an example that at the bottom that we can see that before we enabling a string to a MST string sync, then we need to send out, after we enabling strings in our internal pipes, then we thereafter should send out an allocate payload cyber message to allocate payload on each allocate bandwidth on each DP link to get our string eventually routed to the target string sync. So this figure shows give a rough glimpse of what's the implementation nowadays in Linux code. Let's look at the bottom left-hand corner that while we plug in a load branch, MST branch device into the system, then at first that our driver will probe the topology and to find out all the possible string sinks in the MST topology. Then we will create DIN connectors to the user space. Then user space will later on trigger us to probe the EDIT by sending out the remote I2C read messages, and also send out remote DBCT read message to read out the capability of each output port. Then after automate check and commit tail, then after enabling our pipes for the strings, we also need to send out the allocate payload cyber message to allocate bandwidth from each DP link to each DP link. So ideally at this state, then all string is settled down successfully. And if we unplug a non-root device from an MST topology, then look at the right-hand side. The left connected branch device will detect the disconnection of the output port, then will broadcast upward to the source. Then source will update the topology data structure in the memory, and also fire a hot plug event to the user space. Then user space will later will react accordingly to ask our driver to probe most and capabilities against and do the allocate and deallocate behaviors. And what about that? If we unplug a loop branch device from the system, then there's no more cyber message, which is quite straightforward. Then it will just user space will just ask us to disable pipes, then we will disable strings. Then that at the end, that we will destroy topologic data structure in the memory. And that's the rough whole MST flow in Linux implementation nowadays. So what we did so far to improve the user experience of MST from AMD GPU perspective, that we improve in following different perspective. That first of all is about the MST flow. We were mainly focusing on dealing with problems that we encounter while doing hot plug, hot unplug. And we try to align our code with the design framework. And also we do adjust some code in the design layer to have that align with the specification in DBspec. And as for DSC, which is a key feature to enabling high resolutions, multiple high resolutions modes in MST scenarios, that we were trying to have our DSC be better have better compatibility with different MST hub, because some MST hub doesn't follow the DP spec. And as for DP2, that in DP2 that it brings us a new encoding method as 128 and 132-bit encoding format, and another one is the DSC pass-through feature. Then we also need to adjust our code and also in the end there to support those both features. And as for sustaining perspective, that we are proposing a way to add text into the steps that I just described in previous slide, that we want to record down that whether each MST step get complete successful or not. And based on that, we are developing an IGT, and with that IGT that we will trigger, driver will trigger the hot plug virtually, and then we'll go through all the steps and monitor whether each steps get completed successfully or not. Then based on that, hopefully that we can catch any regression immediately. Okay, so at the end, I will give the demonstration about the scenario that I have an ASIC, AMD ASIC, and plus MST hub with 2 DP output port and 1 HDMI output port, which we use to light up 3 4K 60 monitors at the same time. And for lighting up under these scenarios, that we definitely need to use the DSC. So and later on, I'm going to unplug each monitors one by one and then plug in again. Then you can see that all the monitors get light up accordingly. Okay, then now all the monitors get unplugged, and then I plug in again.